Hello, welcome again. We are solving some questions of machine design. The topic is friction in screw, bearing and clutches. Question number 17 is a single plate clutch used to drive a rotor from motor shaft transmit 42.24 Newton meter torque. Following data refer to rotor and motor shaft. Mass of rotor 1200 kg, radius of gyration of rotor 200 mm, mass of motor, armature and shaft 750 kg, radius of gyration of motor and shaft 220 mm. The driving motor is brought to a speed of 1260 rpm and then suddenly clutch is engaged. Then kinetic energy lost during slipping during engagement. Option A 180.06 kilonewton meter. Option B 150.16 kilonewton meter. Option C 130.12 kilonewton meter, and option D 170.11 kilonewton meter. So here the speed of motor is given as RPM of motor is given as, so angular speed can be calculated, that is 2 pi n by 60, so that will be your 2 pi into 1260 by 60, that is 132 radians per second. Okay, so that is the angular speed of motor, and motor here is your driving part. Okay, so that is the speed of driving part also. And moment of inertia of motor can also be calculated because mass of motor and shaft is given as 750 kg and radius of gyration of motor and shaft is given as 220 mm. So 220 mm. So taking this mass as 750 mm and radius as 0.22 meter, we can calculate a moment of inertia of motor, that is 36.3 kilogram meter square. Okay, and moment of inertia of rotor can also be calculated, that is mass is your 1200 kg. Okay, and radius is your 200 mm. So moment of inertia of rotor is your 1200 into 0.2 square, that is 48 kg meter square. So that is moment of inertia of motor, and that is moment of inertia of rotor. Okay, and the torque transmitted is given as 42.24 Newton meter. So that is 42.24 Newton. So that is driving part and that is driven part. So when the engagement occurs, the initial speed of the driven part is 0. Okay. So and it suddenly attains some speed. So this is your driving. So this is your driving part and this is your driven part, and it is rotating and it is stationary. So after suppose time t, it both will attain same velocity. So its initial velocity is 0 and its initial velocity is initial angular velocity is omega n. So for the driving part, the velocity will angular velocity will decrease, and for the driven part, the angular velocity will decrease or will increase. Okay, so because to have same velocity, same angular velocity. So the final speed of motor is just, suppose alpha m is retardation in the motor shaft after engagement. So that is omega m minus alpha m t, and final speed of rotor is omega r plus alpha r into t. Alpha r is angular acceleration in rotor, and omega r is initial velocity. Okay, so equating these two and putting and alpha m and alpha r can be found out by this. Alpha m t by I m is your alpha m, and t by I r is your alpha r. Okay, so now omega m is initial speed of motor is given as 132. Okay, and now and this alpha r is your t by I r. So torque is same on both the driving and driven part. So now we can calculate t after putting the value. So t comes out at 64.6 seconds. So that is the time when both driving and driven plate will attain same velocity and there is no slipping. So during that 64.6 there will be sleeping. Okay. uh, Second, that there will be sleeping. So now we can calculate the final speed of both the shaft. Final speed of the both of the shaft can be calculated by putting value of t in either of the equation. So final speed is your 42.24 divided by 48 into t. So that is 56.85 radian per second, or it is your 542.9 rpm. So that is the final speed of the rotor. Okay, or we can say motor also. Okay, now to find out, our purpose is to find out the energy loss during sleeping. So that is the sleeping period. Energy lost during sleeping period can be calculated by using that the energy of the driving part minus energy transferred to the driven part. So the energy energy of the driving part is your t theta 1. Theta 1 is the angle traveled during that time. Okay, and theta 2 by the motor, and theta 2 is your angle traveled the during the during that time, during the sleeping period, by the rotor. Okay, so now angle travel turned by the driving shaft during the sleeping period is 64.6, and it is given by formula that is theta 1 is equal to omega t minus of half alpha t square, because alpha is retardation. So and omega m is your 132, and alpha we have calculated here. Okay, now we can find out the angle traveled by driving shaft, that is 6099 radian. Similarly, for the driven shaft or rotor, we can also calculate the angle traveled. So as initial speed of the rotor is 0, and time of sleeping is again 64.6. Okay, and now this alpha r is here same, that is p by IR, so that will be a 1836 radian. So that is the angle traveled by the driver during sleeping period, and that is the angle traveled by the driven during sleeping. So the energy carried by this driving shaft is your t theta 1, and driven shaft is your t theta 2. So energy lost is difference of the energy. So energy lost in friction is your t theta 1 minus t theta 2. So t is your 42.24, and theta 1 is your 6099 minus and theta 2 is your 1836. So that will be your 180.06 km. So answer is your option A.